In this video, we're going over the history of atomic theory. In an earlier video, we learned how atoms have electrons, protons, and neutrons. In this history lesson, we're going to see the important experiments that were performed that led to our current understanding of what forms an atom. When it comes to the history of atomic theory, we must separate it into early atomic theory, followed by modern atomic theory. To talk about atomic theory, we must first direct our attention to Greek philosophers, specifically Democritus. His ideas about the existence of atoms were just philosophical. There were no experiments performed. He just used logic and observation. During his time, Democritus proposed that all matter is made out of tiny, indivisible particles that he called átomos, which is where the word atom is derived. He believed that atoms were eternal, indestructible, and varied in shape and sizes. For example, in his theory, he would mention that water as a substance would be made out of atoms that are round, because in his observations, he saw how water will flow. And in order to have that property, he created a theory or proposal that, well, because of the behavior of that substance, then the atoms that make it must be round. Since Democritus' ideas were not experimentally based, understand that it took about 2,000 years, and specifically, John Dalton was the one that revived the idea that atoms were the ones that will make up the substances around the world, and he showed experimental evidence that that was true. John Dalton created an atomic theory in which he proposed that all matter was made out of atoms, that atoms of the same element are identical, and lastly, that atoms cannot be created or destroyed in a chemical reaction. Later, in 1897, J.J. Thomson performed what was called the cathode ray experiment. And in the cathode ray experiment, he discovered the existence of the first subatomic particle, specifically electrons. Since he discovered that atoms were made of electrons, and he understood that if something is negatively charged, it needed to be balanced with a positive charge, he created what was called the plum pudding model. To illustrate the plum pudding model, let's look at this figure. In the plum pudding model, what he was proposing is that the electrons in an atom, let me just write them in, were embedded in a sphere of positive charge. Later, Ernest Rutherford in 1909 performed what is called the gold foil experiment. And the gold foil experiment actually showed that that positive charge, once proposed by Thomson, was localized, specifically in the nucleus of an atom. Rutherford also was attributed the discovery of protons. Later, Rutherford, since he was able to show that this dense positive area is localized in the nucleus, he started thinking of what does it mean in terms of the positioning of the electrons, which we can see illustrated by those lines. So Ernest Rutherford proposed that electrons will orbit the nucleus, and this completely replaced the J.J. Thomson plum pudding model. The work of Rutherford laid the foundation for the modern understanding of atomic structure. His ideas led Niels Bohr in 1913 to propose that the electrons actually lived in quantized energy levels. He, in his theory, proposed that electrons will be orbiting the nucleus of an atom in fixed paths. Let's look more closely at Niels Bohr experiments in the next slide. We can observe in figure 2.29 a diagram of the energy levels in an atom, okay? That's not drawn to scale. That is just illustrating the idea that Bohr was proposing. The way that he performed his experiment is that he was specifically looking at the emission spectra to observe the behavior of electrons within an atom. When he was performing his experiments, he was specifically using hydrogen gas. The light that was emitted from the light bulb was passed through the prism, and from the prism, it was the wavelength of the light that was emitted was captured in a photograph. And you can see the emission spectra here. Overall, Niels Bohr, in his model, proposed that electrons can climb up and down in these energy levels that you can see them in the dotted lines, specifically in this drawing. And he said that the electrons will be performing this more like horizontal steps in a ladder. Now, the thing is that during that time, he was thinking electrons can move freely inward or up or outward. So overall, even though his proposal worked well for hydrogen, when he moved on to other atoms, the idea and the equations that he created wouldn't support the emission spectra of other atoms. So after the proposal by Bohr, Erwin Schrödinger, with the idea that electrons lived in these energy levels, proposed the Schrödinger equation, which describe how electrons behave as waves and not particles in fixed orbits. He first introduced the idea that atomic structure can be referred to as shells, meaning that the shell in his theory refers to the energy levels where electrons reside. So that goes along the way with what Niels Bohr presented first. Additionally, Schrödinger in his equations presented the idea of a subshell, which the subshell created a subdivision within a shell that determined electron distribution, and he labeled them specifically by letters, which we know now, we know them now as S, P, D, and F. Lastly, these subshells, he actually gave them shapes, which is what we know as atomic orbitals. These atomic orbitals represent a volume of space around the atomic nuclei in which electrons of the same energy may reside. These equations for Schrödinger are so good that to date are still utilized. They predict the location of electrons to 90% accuracy. So thanks to Schrödinger, we can precisely locate an electron by its shell, subshell, and orbital. So currently, we still utilize Schrödinger's ideas in order to locate electrons in an atom.